All right. Hi, everyone. As Gary said, my name is Joakim Elvander. I'm working as a partner engineer and developer advocate for Sony Mobile and Sony in Sweden. You could say that my job is to get people and companies started working on our technologies, our products, that has APIs, basically. But my job is also to advise and help people integrate our products into their environments, basically, to find an overall solution for them. When it comes to Sony SmartEyeglass, this job has indeed been a challenge. Even though it, to me, seems that over the past half year or year or so, the general understanding of what AR is and VR is and MR is has increased tremendously. The customer expectation, if there are any at all, are still a bit more on the sci-fi side than practical as business solutions. Sometimes some of them display more enthusiasm over the technology than really thought through business cases. In this kind of divergent technology, it's kind of suffering from a wait-and-see mindset from potential customers, which is not really unexpected now that the technology is moving forward at such a pace. This creates somewhat of a chicken and the egg problem here. Customers are looking for ready-made solutions that are proven to have a high return on investment. But when they are hesitant to invest, those solutions have a hard time emerging and proving themselves. So I'm doing what I can to nudge these customers, these partners, into taking this leap of faith and starting at small scale with things that we believe should, create this kind of return on investment. So here are some brief facts about SmartEyeglass. It's something that we normally recommend only for use cases that needs in-field of view information and augmented reality, where hands-free context and comfortability is essential. It's not really suitable for mixed reality, and it's definitely not a VR glasses. Today I'm going to have a somewhat awkward talk because I'm going to talk about a customer that declined to let me disclose their name. But I can talk about all the details around the work with them anyway. We're currently running a small-scale remote guidance setup for trials. And the company in question has tens of thousands of employees worldwide. They deliver large machinery installations where they have support deals in place. As often is the case when it comes to companies looking for these solutions, they do have service personnel locally in each country they sell in, but the asset they're short on is, of course, the more senior engineers, the experts that helped out in constructing these machines, that know the intimate details of the machinery. These senior service technicians, let's call them experts, are flying all around the world, helping out with problems that cannot really be handled locally or through a simple phone call, which is causing quite high costs for this company in flights, hotels, compensational pay, downtime for customers, not the least, their kind of satisfaction with this. It also means that their most experienced experts are often more on the kind of older, more experienced side of the scale, and that means that they often have families, or at least want one. So traveling whole weeks at a time is not really, that good for most of these people. Now the good news for this company is that they have embraced the digital age. So nowadays they have mostly system-wide, it is mostly system-wide problems, integration and machinery failures that needs this kind of expert help. They have over the years built up their own in-house software development department, and now the software parts of their installations can be monitored, operated remotely, and so forth. Since a couple of years, this department was looking into ways of helping out with the hardware failures as well, without having to send people. Inspection, repairs, instructions, things like that. thus trying pretty much what we today call remote guidance. They made a couple of iterations on Google Glass a couple of years back. They reached the point where they could, of course, stream video back to a backend server, provide some information in the glasses, as you saw previously here. But as you all know, Google Glass never really delivered when it came to bulk deliveries, and it never really became a product that they could rely on long term. And also had some additional limitations that they wanted to get rid of. So in order to get them started, I agreed to do a proof of concept for them and for similar customers that we could share, where the piece of technology when it comes to remote guidance would be demonstrated on our glasses and APIs. And these include streaming video, of course, using socket connections and VPN to getting video back to the back end, a simple back end, two-way communications, how we're reasoning around that, a UI providing just the vital information for all this, a simple solution where the back end can point out things in the wearer's reality using AR. And I will shortly dig into the details on some of these requirements, but first let me say that it was not entirely easy to boil this down to this short list of things to start with. As with many companies, there are many stakeholders and a lot of people with an opinion when it comes to this kind of project. So about the back end. IT departments have their particulars about how to get through their security and firewalls. And to be honest, we're not entirely in the blue waters yet in this project. Due to this, back-end integration was not really something I could help them out with in this initial showcase. So we settled for a simple demonstration at first using a Node.js backend web server with a custom page for receiving the camera stream, providing chat functionality, etc. This is basically what we're using in the demo outside, if you've already seen it. And though their development team has taken this a bit further, and they've integrated this UI-wise with assets like documentation and stuff like that, that you want the expert to have at hand while seeing this video as well. For the two-way communication part, we reason as follows. There is something that psychologists call emotional bandwidth. This is something used to describe the transmittance of non-verbal communication, which is actually essential to subconscious understanding. It is the information communicated through facial expressions, body language, postures, etc., that we're actually all, subconscious experts of interpreting. It is the reason why emails and social media posts are so often misinterpreted, being harsh, for example. Unless they use emoticons. That's one way of compensating for losing this emotional bandwidth. At the same time, ways of communication that has a very high emotional bandwidth are usually low on information accuracy. Which is why combinations of these different ways of communicating is used in, for example, education. Books are unbeatable when it comes to transmitting like scientific ideas like advanced math, for example. But it needs to be complemented with face-to-face with the teacher in order to reach deeper alignment and understanding of the knowledge transmitted. For remote guidance, the highest emotional bandwidth we can reach is actually through the traditional phone call. Video call is not really practical. The camera is facing forward. And just texting is just a bad choice due to the kind of hands-free requirement, and a keyboard would be required. You could use voice to text and things like that, of course, but that's just a roundabout way. However, this phone call can be augmented by providing the ability for the backend to send text to the wearer for things that aren't really suitable for oral communication, such as parts numbers, 10-digit numbers, things like that you easily get wrong when saying them, and similar identifiers that needs to be exact. So going into the user phase and how we reason there, some managers I talked to in this company were adamant that the glass should show full documentation for the technician. and blueprints in front of the user's eyes, basically. There were even ideas thrown around about using image recognition to kind of overlay and align these blueprints over the machinery. It's not entirely within the realm of the possible with our glasses. And on top of that, I'd like to dig into why this might not really be a good idea. In order to not obstruct the service technician from seeing what he should see, the information needs to be relevant, sparse, and in context. Otherwise, the glasses will induce what psychologists call cognitive stress on the wearer. A Terminator UI like this one may look impressive, but it will probably obstruct work rather than make things more effective. That said, there are places where advanced AR is fulfilling a purpose, so I'm not completely shutting this down, but then it often requires training. Like fighter pilots train with their heads-up displays for thousands of hours so that the information there becomes interpreted subconsciously and muscle memory actually takes over in reaction to the information displayed here. This is also one of the reasons why many car manufacturers are a bit hesitant about heads-up displays for, for drivers. They're not used to this kind of solution and might actually distract them and cause an accident. I know there are some car companies still experimenting with this. This sample I took here is from a drone control app that we developed for our glasses, where keeping your eyes on the drone is vital. And only useful information is shown in the glasses that actually adds to the user's awareness of the operation of the drone. For the remote guidance UI in the glasses, we thus finally agreed that less is more. The watch here in the image is basically just used for, gesture operation of the drone. It's just a gimmick, basically. So, how did they arrive at working with our glasses then? Augmented reality or in-field of view graphics, we believe, is best suited for when it's important to actually see the real world, but where there is a need to either superimpose extra information or where it's simply, comfortable to have the information in front of you without overly obstructing your view and without needing your hands to retrieve that information, as a smartphone or a tablet would require. Mixed reality, which we don't support in our eyewear, as I said, but very much so in our tablets and smartphones, is good for visualization of 3D models that you attach to an anchor in the real-world environment. But if you think about it, what you're actually watching is that 3D model. Reality is just a backdrop then, and that can be obstructive if you're supposed to actually see what you're working with. In this case, at least. Now, the interesting thing is that glasses capable of mixed reality is often capable of doing exactly what smart eyeglass can do as well, due to the more advanced and expensive technology, at least in theory. In practice, however, there's often a world of difference in how you develop for these, and the state of this matter would actually make a quite interesting talk in itself, but it would definitely be more on the techie side of things. And one should be aware that even though mixed reality looks really impressive and so on, I mean, side-screen glasses, in-field of view glasses, or mixed reality glasses, they all fulfill different purposes, as VR as well, of course. So you need to choose wisely, not just the one that impresses you the most. As mentioned previously, they experimented with side screens early on, like Google Glass, which can be a really good choice when it comes to purely textual or visual information that is not necessarily anchored in the real-world environment. Smart eyeglass can fulfill, arguably, the same kind of use cases that side-screen glasses can do. But a side-screen solution is not really the optimal choice if you want to do an augmented reality solution of some kind, like remote guidance, which is almost by definition in-field of view technology. So hence, they decided to try our glasses, and I promised them some help in engineering this kind of solution. So now I'm going to go a bit techie on you, and I hope there are enough engineers out there to not fall asleep during the next few slides, but I tried to skip through this kind of fast. AR allows you to annotate reality with graphics. That much we established. Now, there are many ways of doing this depending on the business case, but some are still pretty sci-fi and expensive to implement, such as automatic object recognition, and through that, automatic annotation of objects in reality. And so far, I've only seen questionable value in doing this compared to the investment needed, actually. Unless it's about finding a flat surface, or in mixed reality, finding an object to anchor your 3D object to, or recognizing QR codes in the environments, OCR, things like that. We're talking about deep neural networks in order to recognize cats, for example, or a certain machine part and things like that. And that needs months of training to recognize a single object. And it requires thousands of images of that object with different backgrounds and from different angles. The outcome is not 100% foolproof either. So technically, it's definitely possible. I'm sure we're going to see more use cases of this in the future. But if we're talking about today, I have still yet to see a good return on investment on this kind of technology for wearable glasses. What was possible in this case, though, was to let the backend click on the video stream and mark items in the wearer's reality for him. It's a kind of virtual pointing of a finger, compensated for the expert not being there in person. The coordinate of the click on the video stream is translated into glass coordinates and further on to world coordinates, where we should place this marker in a system around him. That should be displayed in the wearer's reality. The AR system in SmartEyeglass works by creating a cylindrical coordinate system around the wearer. It can be seen as a virtual glass cylinder with a set radius, basically the viewing distance. And it's put around you when wearing the glasses, basically. On that glass surface, you can put objects at certain compass directions and at certain elevation. The screen of the glasses allows for drawing graphics at 20 degrees of the user field of view, diagonally. And the camera is facing in roughly the same direction. So that means we need some kind of calibration in how the center of the screen relates to the center of the camera image. Calibration is simply done for a pair of glasses by centering the middle of the screen on an object. The backend can click on that object, and thus you get the coordinates of it, and that can be used as an offset in calculations later on to see how these two centers align. This alignment, however, is only valid at long distances due to what we call camera parallax. That is, at long distances, the angle from the camera to the object, the camera is slightly to the side in our glasses, and from the center of view of the person wearing the glasses is almost the same. While at close distances, it's definitely not the same, and that needs to be taken into account. The difference in field of view between the glass screens and the larger camera field of view also means that the user may need an indication of where the marked item is. If it's on the fringes of the camera field of view, which is outside the screen field of view. So we introduced the concept of a compass. This compass would indicate where the user should turn his head to see where the action is, so to speak. And it would also have the secondary purpose of functioning like a sight for the middle of the screen when you were in the calibration phase. By knowing this, sorry about this, I'm gonna skip through this fast. By knowing the camera field of view, the coordinates of the click point, the calibration of the center of the camera with the center of the screen, the click can be translated to screen coordinates in order to point the compass. By knowing the head direction, what the Android API called the rotation vector, we can record which direction the user was looking with the glasses at the time when the click occurred. And then we can calculate and offset this angle by knowing the angle per pixel of the camera, so to speak. And that information then can be used to place this marker on the cylindrical coordinate system. Now, this actually simplifies some additional physical properties of the camera and the lenses. such as aberrations, for example. That is, that light gets bent a bit slightly differently at the edges of the lens. And we're also looking at the camera image as a flat surface, while it's actually, the recording of a 3D environment. But those errors aren't really large enough to merit more complex calculations like this, because it's with very, very little gain. For near-field view, we are currently working on how the UI would best look like in that case, to set the approximate distance to the objects looked at. The best thing would be, of course, to have an accurate measurement of this through sensors in the glasses, but since this version lacks such a sensor, it needs to be set manually. This is probably not adjusted very often in this use case, though. You either work at arm's length or at further distances, basically, from what we've seen in their use cases. So a simple switching of modes between near and far could be enough with a small adjustment of distance. We're not quite there yet on how to do this, but as long as we know the approximate distance to the object and we know the definite distance between the center of view and the camera, we can get the formula presented here, from which we can then further derive the angle offset that I talked about earlier, at which we need to place the object, still the alpha in this equation here. So, that was that. We're out of the math here. Now let's go into the outcome so far in this project. Drawbacks first. We're using a magnetic compass, and it's not always accurate enough. It fluctuates like plus minus 6 degrees. It tends to have some noticeable latency, like almost any compass has. But since we're mostly calculating differences, offsets to a rough direction, and as long as the compass is not fluctuating too much, it's definitely, enough for this kind of large machinery. The movement of the wearer's head, as well as network latency, means also that the backend usually has to click several times anyway to zoom in on the object that you actually want to talk about. So this loss of accuracy at the image, at the fringes of the image due to aberrations and so on is actually less of a problem due to this. It would definitely be a problem, though, if we had different use cases like microelectronics or something that would really, require pinpoint close-by accuracy. Then we wouldn't be able to handle it this way, at least. During the work with this, we also came across a number of other practical solutions for the use case, around the use case. Networking, we've kept simple so far. We'd like to keep it to at most a VPN supported by the phone for this, the data connection. Battery life is another thing. We have 2 to 4 hours normally for constant operation with these glasses, but you can connect a small external battery to the USB port on our puck, which actually fits quite well in a service technician's vest pocket or something like that. And through that, we've actually reached up to 18 hours of operation time. For our glasses, the phone is required. It's actually the phone that does the heavy lifting. It's an Android app running on that using an extra API to show information and read the sensors and so on. But that's not really a problem in this case. I mean, they need the phone for the oral communication, and it does in fact provide unmatched connectivity and optimized antennas and everything. So the outcome then. As I said, we're still in initial trials so far, but they have to this date saved several trips, on an average 8 hours of travel time saved per incident. And that means that the customer got up and running basically 8 or more hours faster. That could equal money, for the customer. The project is basically already paid for itself, in this small setup at least. Not the least when counting in the customer satisfaction and getting up to speed faster and so on. Reception has been really good for the service personnel. Networking being the by far biggest issue. Cell data coverage, quirky Wi-Fi, things like that. And the reception from the experts that have tried this in certain cases is also very good. Mainly, as I said, for family reasons. But, well, at least to one person I spoke to, it's actually a problem that he doesn't get this compensational pay. He kind of relies on that. So that's worrying him. And the next steps here is, of course, as I said, a close proximity UI is something we need to work on. Using the built-in voice control that we have in the glasses for taking snapshots for documentation, for example, is a feature we're investigating. And we need, of course, more months of, I mean, we only have a couple of months of evaluation so far, so this needs to run along a bit more to see the certain return on investment for this. So that's it from me. We have the demo part that I wrote for them running outside in case you guys haven't seen it yet. So you're welcome by our booth to see it running if you want to. I can take questions. Yes, sir.
I like the fact that you're making use of both the phones and the glasses.
Mm-hmm.
But have you thought about creating a software solution that seamlessly integrates the two? If you look back to the ad code video, it worked great with the glasses, and it was stepping the person through the inspection, until it got to the point where it was a fail. And now he has input data to say, here's the error code or whatever. So what would have been really slick is if he can say, switch the phone, and it would seamlessly switch the phone, and we could then input data there. I kind of see the glasses as a way to consume data and to interact. And the phone could be the place to produce data.
Right. So the question was basically whether there is a way to interact with a phone instead, as a fail-safe, right? Actually,
it's not necessarily a fail-safe. Is that if I'm trying to input data or produce data, then I can go to my phone. And I can consume the data through my glasses. So it's a seamless software solution that uses the platform that makes the most sense given the task that I'm.
That's absolutely possible because this app is actually running on the phone. It's just using the glasses as a display. So it's perfectly capable of having its own UI on the phone for more advanced, entry of data or whatever. But on the other hand, you would lose the kind of hands-free thing, right? So you would have to question whether it's better to have the glasses, completely hands-free, or if you can make do with just the phone in that case.
I think we need both.
Yeah. Well, they're complementing each other. It depends on the use case. Very much depends on the use case.
Wait, just introduce yourself.
Carrie Thatcher, Lieberstream. I want to comment on what this guy just said. I think that the idea of dual modality is absolutely correct.
Could you speak up a bit?
I think the idea of dual modality is absolutely correct. If you think about taking pictures of rotating machinery, for example, and you're sticking your head inside of a turbine, it's a bad idea, as opposed to picking up a phone and doing this.
Yeah,
so
absolutely.
Our experience says that that is an absolutely correct
I mean, it's always a question about using the right tool for the job.
Yeah.
I mean, sorry if I'm interrupting you now, but for example, we've been working with parts picking situations as well. And we had one customer requiring us to have the glasses recognize barcodes and QR codes in order to scan them. They wanted to get rid of the hand scanner, basically. And we told them, well, it's not really a good idea, but okay, we can do that. It's not, not that hard integrating that kind of library. And that made them discover for themselves what an ergonomical nightmare it was to twist your head around to scan these codes in large boxes. So yeah, you're definitely right. You shouldn't, stick your head in the machinery with this kind of solution. Okay then, thank you very much.